Now, I have given you this homework while discussing the conjugate directions method in one of the previous lectures. Now, I will solve this part of this homework, this part, but I will keep this for you to try out. So, today I will begin by trying to solve. So, what I have to prove is the conjugate directions and the gradients are perpendicular to each other, but so what I have to really prove is the following: is gk di at any k is equal to 0 for all I for all I which is bigger than or equal to 0 or less than or equal to k strictly. What we do is that we use induction. So, by induction what we show is the following, that we show that let us assume gk di is equal to 0 for all, and to prove gk plus 1 di is equal to 0 for, so that is exactly what we have to do. So, we have assumed this. Now, let us start working it out. Let us observe this fact. Now, this one is very simple, since gk is nothing but h x k plus b. So, gk plus 1 would be nothing but h x k plus 1 plus b. So, b would get cancelled out, and this is what you will have. Now, of course, you know that x k plus 1 is x k plus alpha, that is how you update using the conjugate gradient direction, that is how you update alpha k dk. So, then gk plus 1 minus gk, now I can write this as alpha k dk. So, it will become alpha k h dk. Now, I multiply both sides by, rather I take the inner product both sides by di, right, for I. So, then I will get gk plus 1 di is equal to gk di plus alpha k di h dk. Now, I have to prove this fact. So, basically I have to prove that for all I equal from 0 to I equal to k, this thing holds. So, first put I is equal to k and imply that plus alpha k dk h dk. Now, you know what is alpha k? Alpha k is already, you have solved out alpha k. Now, what we have to do is, now here I have to put the value of alpha k. So, alpha k is already known to me, and that is minus gk dk dk h dk. So, if you do that, so then gk plus 1 dk is nothing but gk dk minus orientation, so that you can follow it, gk dk this, and now here also we have dk h dk, which cancels up. Now, h is positive definite matrix. So, it will, this dk is non-zero. So, these are all positive. So, this will cancel up, and so we will be left with gk dk Now, once you have done this, this is 0. So, you have proved for k, now you have to prove for anything other than k. Now, consider I strictly less than k, then for that gk plus 1 di is gk di plus alpha k, I strict alpha k, you will come here di h dk. So, since I is strictly less than k now, so our di is not I is not equal to k. So, then by the fact that these are conjugate directions, this would become 0, and the fact that we have already assumed when we started the proof, then this would also become 0. So, ultimately this proves the fact. Now, what is important to know that all these things that we have done, all the conjugate direction or conjugate gradient method have been really applicable for convex problem, that too with H, a convex quadratic problem with H positive definite, means really strongly convex or strictly convex quadratic problems. What about handling it for non quadratic problems or anything? It is a for any sort of convex problems, for example, can we do something with that? So, for that Fletcher-Reeves introduced a method called the Fletcher-Reeves method. We are just going to outline this method here. Now, let us write down the Fletcher-Reeves method step by step. This can work for non quadratic problems also. Actually, the shift from linear to non-linear is quite a difficult shift. The methods, not once you have non-convex problems, you have very less things available to you. You just make a trial with whatever algorithms you have in your hand and see what you have. That is the only thing that you can possibly do. And recent research there are efforts to take those points and try to give some quantitative justification about their behavior, but that is absolutely at the frontier of research. So, we will not get into that issue at all, but I just want to recall and remind you that non-convex optimization, by the way, is very hard. Of course, there could be convex optimization problems which are also not so easy to handle, but there are algorithms which will support them, but for non-convex problems you just do not know in large cases what to do. We will learn about sequential quadratic programming methodology as we go along, but you see that has its own drawbacks as we come to it. Now, in Fletcher-Reeves method, so step 1 is to initialize your starting point x0 and tolerance epsilon. Step 2 is to set k is equal to 0. Step 2, we should compute G0, that is the gradient at x0, and set the first conjugate direction, that is set step 3, we do the most idealistic stuff, find alpha greater than 0, which minimizes of course, this minimization is done in an approximate way. So, here you have one dimensional minimization, We have not spoken much about one dimensional minimization in this course. Possibly at the very end of this study about unconstant optimization, we will take up one day to explain some very important one dimensional minimization techniques, because when you want to solve this problem where x k and d k are fixed, then this is nothing but a function in alpha. So, then basically you are talking about one dimensional minimization of a real function in real variables. So, f from R to R. And once you have done that, so that is alpha k. So, basically find alpha k, I should say, which minimizes this. Set your next iterate to x k plus 1, and x k plus 1 is x k plus alpha k d k. Is that I really do not know the solution, but when the distance between x k plus 1 and x k, this distance, that distance becomes very small, that is we are basically coming near the solution. Like if you had thought about steepest distance. So, there was this is your level curves, suppose. So, say therefore, so level, and so what would happen? Level curve means these are the function values f x y equal to c, because we are in 2 dimensional setup, you can see it very well. So, you are here. So, you take one direction, you moved here, then you took another direction and you moved here, then you are moving there, and then you are moving there, and then you are moving there, and then here, then here, then here, then here. So, as you go near the solution, this distance also decreases. Let me also give you an explanation that, so if your thing is actually taking you to the solution, then this is what should happen, that is if x k is going to the solution x star, then this is what should happen, because then what I can do is I can write x k plus 1 minus x star, this is equal to plus x star minus x k, and this is nothing but less than x k plus 1 minus x star plus x star minus x k, and this this whole thing now goes to 0. So, if I can show that the distance between these two consecutive ones becomes very small, basically I am trying to show that it is a Cauchy sequence essentially in some sense. So, if I can show that, then I know that it will converge, that it will actually go to towards the solution. Right. So, for k sufficiently large, we can if we can show that this is true, this distance is very small, then I am almost near the solution, then I can stop there. So, what I do now, x k plus 1 minus x k is equal to alpha k d k, and norm x k plus 1 minus x k is equal to alpha k d k. So, basically you really do not have to bother about x k plus 1 at very first, you just take alpha k d k, check if norm alpha k d k is strictly less than epsilon. Step 4. So, there are two answers to it, yes and no. So, if it is yes, stop and take x k plus 1 as the solution, approximate in fact, as the approximate solution I should write. If it is no, then do the following. There comes step 5. If k is equal to n minus 1, right. Set x0 is equal to xk plus 1 and go back to step 2. If k is equal to n minus 1. So, we have not reached our solution in n minus 1 steps, then we have to again restart the procedure. If not, else compute gk plus 1 and beta k is equal to gk plus 1 gk plus 1 gk. That is a nice one. And then you compute the next direction dk plus 1, because from there xk plus 1, now you have to go to xk plus 2. So, you are computing the dk plus 1 is equal as minus gk plus 1 in the same way we have done for the power of this Hestenes's conjugate gradient method plus bk to dk. And you see now once you have that, what you can do is set k is equal to k plus 1 and go back to step 3 and go back to step 3, or rather assign k equal to k plus 1, okay, go back. So, this is an approach. See why this k equal to n minus 1, because in the quadratic case when you have positive definite Hessian in n minus 1 steps, you are basically getting the solution. So, in n iterations, basically n iterations you are getting the solution, and here I am in n minus 1th step and I am yet to get the solution. So, I have to reset x naught as x1 and take it at the starting point and start the whole procedure again, right, because at k is equal to n minus 1 I have not got the solution. So, this is some sort of slight restriction that is there. At k equal to n I am supposed to get the solution, and I started from x0. So, I have x0 then in n steps. So, xn minus 1 would be my just a moment. So, as we have already seen in our previous studies that in n steps, in the case of when h is positive definite, in n steps we are coming to the solution. So, this we can come to the solution in just n steps, right. We start with x0 and xn would be x star. So, here when k is, you can say why k should not be n minus 1, but I have started with k equal to 0 and I have come to k equal to n minus 1, which I have, so I have taken n steps, right, 0th step, first step, second step, third step, nth step, n minus 1 is the nth step in this case. So, I have reached the nth step. So, even if I have reached the nth step, so xn should be my solution. So, here I have reached the nth step, but I have not got the solution. That is the, if k is that is the whole idea. If k is equal to n minus 1, so I have already taken nth, k is from 0 to n minus 1, I have taken n step, this is the nth step, and 0th iteration, the first iteration, 0th iteration, first iteration, second iteration, k n minus 1. So, basically I have taken n steps, I have got my come to my n minus 1th iteration. In the next iteration I am supposed to get the solution, but at k equal to n minus 1, if I do not get the solution, then I really have to restart the procedure. That is because we are handling non-convex problems, we are not sure whether at nth step we are going to get a solution. We are not non-quadratic problem, we do not know anything about the function's nature. So, then a little bit of extra risk caution is kept here by putting k is equal to n minus 1 and then again restarting the whole procedure from x naught equal to xk plus 1. Now, we are going to end our discussion of conjugate directions and conjugate gradient method with this very important class, and then we will go into a very slightly interesting problem called the least square problem. Now, what does this least square problem means? So, least square problems is how optimization can help you in solving equations, and let us just see what we can do about it. I have an m cross n matrix and I want to solve this equation. So, A is m cross n matrix and x is an n vector and B is in Rn. So, now this need not have unique solution, it depends on the relation between m and n. So, in general it can have many solutions, and it is not, I do not know that there is because m is not equal to n, I have no idea about invertibility in this case, and so I cannot really figure out what is the solution so easily. It is not so easy to figure out one solution even. If B is 0, then okay, x can be 0, then one of the solutions. If B is non-zero, I do not know. How do I attempt to solve this sort of system of equation, because these things come up very much in applications. See, what I can prefer to do instead of trying to solve it, I construct this function is called the residual function. So, if I take an x, I take any x in Rn and put here in and multiply it with A, then if Ax is not equal to B, if it is not the solution, then Ax minus B, this vector is a non-zero vector, and then the norm of that would be non-zero. So, if x is not a solution, then so this quantity is called the residual. This quantity sometimes, for the more terminology loving person, is called the residual. So, x is not a solution, then this will happen. So, if x is a solution, Ax minus B would be equal to 0, and then that x would actually be the minimum of this problem, because this is always greater than equal to 0 for any x for which Ax minus B is Ax is equal to B, that x must be a solution of the minimization of this problem over Rn. So, if x star solves Ax equal to B, if and only if x star solves the problem minimize Rx, x element of Rn, where Rx is in this case now. How do you, so if I want to solve this problem, I can actually solve this minimization problem, but how do I prove that? If x star solves Ax equal to B, then naturally Ax star is equal to B, and R x star is equal to 0. Hence, R x is greater because R x is greater than or equal to 0 for all x. So, R x star. So, x star minimizes R x. Now, if x star minimizes R x, how do I show that you have this as the solution? If x star minimizes R x, then that x star would solve A x star equal to B. So, if x star minimizes, suppose x star minimizes R x, then if x star minimizes R x, then what would happen? I can write that the gradient of this problem must be 0. So, I have already known that x star is minimizing R x. So, gradient of f of x star, so that would give me A transpose A x star minus B is equal to 0, or A transpose A x star is equal to A transpose B. Okay, that's what it gives me. What I have found here is actually a critical point. So, if this happens, then this is, if this happens, then this is what will happen. Then can I say here that A x star is equal to B? From this, can I say that A x star is equal to B, which looks quite clear. Now, suppose A is of full rank, A is of full column rank, right? Then A transpose A is actually invertible. Then you can write x star, if A is of rank n, that is A is of full column rank, right? If A is of rank n, then x star is equal to A transpose B. Now, if I can get this, so if x star solves this problem, then grad f x star must be equal to 0 and x star must have this form. Then if A is of rank n, then x star must have this form. Then what I have? Then A x star, then A of x star is equal to A of A transpose A inverse A transpose B. See, because A is of rank n, A transpose A becomes a positive definite matrix. That is very important, and that is why it is invertible. So, if A is of rank n, is a positive definite matrix. So, they prove this in the homework. So, this is your homework. Okay. Now, what is Ax star? So, let me see what happens. So, now this can be written as A inverse, A transpose inverse, because AB inverse is B inverse A inverse. So, this is A inverse, A transpose inverse B. This is identity and this is identity. So, you have Ax star is equal to B. So, I will now modify what I have written. So, this is how you discover things in mathematics by trying it out. So, I have not written it purposefully, but what I have now done, what I have written? I have written that if A is of rank n, let, so my result is let A be of rank n, of full column rank, then X star solves Ax equal to B if and only if X star solves this problem. Then, so you see, then now we have the full result. Now, this is my result. So, basically now if I want to solve this problem, what I will first do is I will first find a point like this, right, and then if A is of rank n and if I am now trying to minimize this problem, if I find a critical point of this problem, any the critical point of X star, if A is of rank n, critical point of Rx, sorry I have written, it should be Rx, critical point of Rx is of this form, and we want to show that this critical point is actually a minimum. This critical point is actually a minimum, that is very, very important to show. So, R of x is norm Ax minus B whole square. So, take any x in Rn. Now, once you know this, you can write this as star minus B. Now, this term would be 0 because of this fact, because we know that if X star is a critical point, if X star is a critical point, if X star is a critical point, so the critical point of this least square problem, if I minimize this, if I find this critical point when a rank of A is n, then that critical point is actually a solution of this problem, and we have shown that that critical point is actually solving the original problem Ax star equal to B. So, if I can, so it is very nice that I can actually in an exact way I can find, I have an exact analytic expression for this, and that is a beautiful part which you do not always have in optimization. So, if X star is a critical point, then what you have, so the derivative, I have again made a small mistake in my writing, but please forgive me for this because this is something you can figure out, because here instead of f it should be r, because we are trying to find the critical point of r. So, then grad Rx star is equal to 0, and again I leave it as a homework for you to figure out that the derivative of Rx, that is it's your homework to figure out that the gradient of Rx is nothing but A transpose Ax minus B. So this implies A transpose Ax star minus B is equal to 0. Now, if you look at the expression 2 or Ax minus Ax star, so let me just forget this 2, Ax star minus B, then this is nothing but A into x minus x star by matrix property and Ax star minus B, and that is equal to x minus x star A transpose Ax star minus B, and that is, you already know, it is 0. So, this is 0. So, now this is 0 and this is greater than equal to 0. So, what we have proved, that we have proved that Rx is greater than equal to Rx star, which is this part. So, this is your Rx star. So, hence x star is the minimum of Rx. So, any critical point, there is one critical point, the critical point of this function is actually a minimum of this and is also a solution of the equation Ax star Ax equal to B, provided A is of rank n. So, this is a very, very important requirement of rank n. So, if some little bit of extra things that we have, if you put in some little assumption, things flow in a much more interesting way. Okay. So, tomorrow we will start in the next class by talking to you about the Gauss Newton method and talking to you about the least square problem in a more general way. This is just an example to show you the importance of the least square problem, how optimization can be used even to solve a equation, this linear equation. So, and then we will discuss a bit about Gauss Newton method, and after that we will start talking about the quasi Newton method, and then return to theory for a while and then get into return to theory for a while for the unconstrained case and get into the study of the celebrated Kuhn-Tucker conditions. Thank you.